22 Mega Regents Review for Chemistry. This is Mrs. T. In this video, we are going to go over the topics that you have requested. So the first topic was atomic, having to do with isotopes. When we're talking about isotopes, we are talking about, sorry, I'm going through my reference table here. We are talking about atoms that are of the same element. Since they're the same element, that means they have the same numbers of protons and the same symbol, but they will have different numbers of neutrons. Now, these isotopes, for example, could be one of the often ones, the sets that we often see would be like carbon-12 and carbon-14. If we look on the periodic table, carbon has the atomic number 6. If we do mass number minus atomic number, we get neutrons. So each of these has 6 protons, but when we add the protons and the neutrons, we get a different number. So anytime they ask you about isotopes, it's atoms of the same element, which means they have the same number of protons and the same symbol, but they're going to have different numbers of neutrons. Bright line spectrum, remember that we have 2 different types of electron configurations. We have ground state, which is the lowest energy state. The ground state is also found on the periodic table. If an atom absorbs energy, the electrons can move up to an excited state, which is temporary. And then when the electrons move from excited, right, which is a high energy state, back down to ground, which is a low energy state, energy is released as light. This energy that's released as light can be separated into the bright line spectrum. Can be viewed as a flame test. Is what gives us our color in fireworks, among other things. Ions versus atoms. Remember, the word atom means neutral, which means that the protons and electrons are equal. Ions will have either lost or gained electrons. Remember that losing electrons makes for positive ions, and gaining electrons makes for negative ions. Metals tend to lose electrons to become positive ions that are smaller, and nonmetals tend to gain electrons and make larger negative ions. Nuclear alpha decay is going to be, you'll have your substance, your element, and you will give off 4 over 2 He plus, something here and something here and an element. We set up 2 separate math problems. So for example, if we want to look at table N for natural nuclear. We can find something that undergoes alpha decay and plug that in here. And for example, plutonium-239 undergoes alpha decay. It has alpha as its decay mode. We're going to look up plutonium-239's atomic number, which plutonium is at the bottom of the table and has an atomic number of 94. Alpha, beta, and positron decay are all natural, which is why the plutonium-239 is on its own before the arrow. So now we're going to set up two sets here. 239 equals 4 plus 235. 94 equals 2 plus 92. And then we look on the atomic number 92 on the periodic table, and that means that plutonium-239 undergoes natural transmutation and turns into uranium-235 by alpha decay. If you want to know about beta decay, we can pick one like potassium-42, which says that it undergoes beta decay. Remember, we can look up these symbols on table O. And so that's the beta. 42 for potassium. We do need to look up potassium's atomic number to stick that in there. And potassium's atomic number happens to be 19. So now again, we set up these two math problems. 42 equals 0 plus 42. 19 equals minus 1 plus 20. And then when we look on the periodic table, that's calcium. So that means that potassium-42 transmutates into calcium-42 by beta decay. Now, you didn't ask about this on your thing, but positron would just change, the particle that's after the arrow to a positron, which would be 0 over plus 1e. When we talk about alpha, beta, and gamma, alpha has the least penetrating power, but it has the most ionizing power. Okay, so both of those go for alpha. And then if we look at the rest, gamma has the most penetrating power, but the least ionizing. And that's also because gamma has no charge. If we also wanted to separate alpha, beta, and gamma, and actually I should do it this way. I should do alpha, gamma, beta, because otherwise it's going to make my lines all messed up. If I push them out here and there is an electric field with negatives and positives, gamma will go straight through because it has no charge, it's not attracted. Alpha has a positive charge, so it will go towards the negative. Beta has a negative charge, so it will be attracted to the positive. Okay, opposites attract. Gamma has no charge, it will not be attracted. At any time, you can pause, rewind, and re-listen. I'm going pretty quickly just because I'm trying to get this video made, but if you need to, you can always pause or rewind. We're talking about distillation. Distillation, remember, separates mixtures of liquids. By boiling point. Lowest boiling point is always collected first, and boiling point as it relates to intermolecular forces, stronger intermolecular forces leads to a higher boiling point because it requires more energy to separate the molecules, atoms or ions or whatever they are from each other in order to go from the liquid to the gas state. So the one that would be collected first in distillation would also have the weakest intermolecular forces of attraction. Periodic table trends. Remember, we have our friends francium and fluorine, and hydrogen and helium. Remember that hydrogen is a nonmetal. It's just up there because it has one valence electron. Remember that groups 3 to 11, okay, not 12, are transition metals. These are the ones that make colors when they make ions. Our staircase of metalloids is over here. Everybody down here is a metal. And everybody over here up to the staircase and over that way is a metal. Fluorine group there is our nonmetal. Group 16 is mostly nonmetals. And don't forget, here it's boron. Get rid of this little squiggle here. It is boron, silicon, As, Te, Ge, and Sb, right, that are our metalloids. Okay, these are our metalloids. Metals are on the left of those and down. Non-metals are on the right and up. Remember that francium is our biggest loser. Francium loses electrons the easiest and has the largest atomic radius. Fluorine is the one that gains electrons the easiest. But helium is the smallest atom. If we're looking at our trends, again, electronegativity and ionization energy increase towards helium and fluorine. Radius increases towards francium. And francium is the most metallic. So down and to the left is more metallic. Fluorine is the most non-metallic. So most non-metallic is up and right. If we want to talk about the reasons for the trends, anytime you're talking about a trend across a period, it's because of increasing numbers of protons or increasing nuclear charge. Nuclear charge, remember, is positive and it's based on the number of protons. Anytime you are going down a group, the trend is because of increasing numbers of shells or more shielding. When you are going to be looking up those trends, you're going to use table S, attraction for electrons is electronegativity, energy to remove is ionization energy, and then size or radius, you're going to look up atomic radius. Periodic table allotropes, this is going to be like oxygen, which is O2, versus ozone, which is O3, or if they mention diamond and graphite, or they mention the different colors of phosphorus. I think I spelled phosphorus wrong, don't judge. They are different forms of the same element, okay? And these different forms of the same element have different structures. Which gives them different properties. Okay, they're going to have different physical properties. They're going to have different chemical properties. They're going to react differently in different types of chemical reactions. Remember, we are going to use, or we are going to breathe oxygen. I fixed phosphorus. We are going to breathe oxygen as O2, but ozone is not able to be used for our cellular respiration. Bonding, ionic versus covalent. Remember, TICs, transfer, ionic, covalent, share. Ionic is going to be metal plus nonmetal with transferring of electrons, like Na giving its valence electron to Cl. We draw it with brackets. Na becomes +1 because it lost. Chlorine now has 8 valence electrons with a -1 charge. Whereas if we're talking about like water, two nonmetals, the electrons are shared, hydrogen and oxygen. This is going to be 2 valence electrons plus 6 valence electrons. We can use HUNC. Hydrogen and halogens make 1 bond. Oxygen makes 2. Nitrogen makes 3. Carbon makes 4. We can use that, or we can use happy minus have. Stable number minus valence electrons tells you how many bonds. Oxygen is going to make 2 bonds, 1 with each hydrogen. That is 4 of our 8 electrons. Oxygen gets 2 lone pairs. And again, in particular, water has a polar shape. It has a negative side and a positive side because it has an unequal charge distribution. Water has a polar shape. Polar bears swim in water. Other polar molecules will also dissolve in water. Balancing equations, for example, if we want to do H2 plus O2 makes H2O, we are going to put coefficients in front. And we can see that there are 2 hydrogens on each side, but there's 2 oxygens here and only 1 oxygen here. So we are going to put a 2 here to make it 2 oxygens on each side. Now that gives us 4 hydrogens, which means we're going to put a 2 here to give us 4 hydrogens over there. And on any blank when you're balancing, you're going to put a 1. It's called balancing by inspection. You're going to just do trial and error with numbers in front to make sure that you get the same numbers of atoms on each side. Mole conversions, for example, if they give you 24 grams of carbon and they say how many moles, you can do this one of 2 ways. On table T, there is a formula that says number of moles is equal to given mass. Oops, I wrote give mass. Over the gram formula mass, or we can use dimensional analysis. So if we just want to put this over the gram formula mass, then we get 2 moles. If we want to do dimensional analysis, 24 grams carbon times 1 mole over 12 grams still gives us 2 moles. If we're given, 6 moles of N2 and they say how many grams, we can either just do 6 moles N2 times 28 grams over 1 mole, and then when we do the math, get the answer. Or we can plug it into here, and this is where my given mass would be my X, would be 6 moles equals X over 28. Either way, we're still multiplying the number of moles times the gram formula mass. Mole problems, if we go back to our balanced equation from before, how many moles of this can be produced if this many moles of that For example, how many moles of water? You can put an X over your water. If 4 moles of oxygen completely react, we get 4 over 1 equals X over 2 if we make that into a proportion. Right? Word problem, how many means X. 4 moles of O2, put it over it, make a proportion. Or dimensional analysis, we do 4 moles O2 times the one that I'm looking for, coefficient of water is 2, over coefficient of oxygen is 1, and I cross out my O2s, and I still wind up with 8 moles. So it's either proportion, putting the word problem over the balanced equation, or it is you take the number of moles they give you times the coefficient of the one that you want over the coefficient of the one that you started with. Hydrates, for example, CuSO4 5H2O. Maybe you're being asked, it says that there is 16, no, let me not do that. Maybe you're being asked to find the percent water by the formula. In that case, you just find the gram formula mass, which is going to be what, 63.5? You know what, let me do this right from the reference table, so in case you're following along. So you're going to find the gram formula mass. I think I told you guys to round to the 10th. Let's round it to the 10th. I apologize that I'm doing so much scribbling here. 32.1, 64.0. Water is 18, so that's 90.0. We add all of this up. We get the gram formula mass, 63.5 plus 32.1 plus 64 plus 90. And we get, try that again, 63.5 plus 32.1 plus 64 plus 90. We get 249.6. That's your molar mass. Percent of water would be 90 divided by 249.6 times 100, and whatever you get, and then you put percent after it. Or they can ask you, we start with a hydrate, and it has a mass of 6 grams. We heat it until we get our dry, and the anhydrous, let's say, is 5.5 grams. And then they ask you for the percent of water. 6 minus 5.5 is 0.5, which would be your water. So we would do 0.5 over 6 times 100. And whatever answer you get, you would put percent after it. Kinetics equilibrium, Le Chatelier's principle. Remember, if we have a reaction like, I don't know, N2 gas plus H2 gas in equilibrium with NH3 gas, we have to balance it. It would be given balanced to you. Remember that you also might want to know where your heat energy is, because that's going to help you with any of your questions about adding heat or increasing or decreasing temperature. So in this case, it happens to be an exothermic reaction. Remember that when we're at equilibrium, we are at equal rates. And we have constant concentrations until a stress is applied. Le Chatelier's principle says that a stress will cause equilibrium to shift in a way to reduce that stress. And our waves are add away, take towards, increasing pressure, shifts to less gas. Add away and take towards can be used for concentration as well as temperature, because increasing temperature or decreasing temperature is like adding or removing heat. If we happen to, in this reaction, if we add N2, remember it's the arrow that splits between the left and the right. If we add N2, we shift away. That will cause shift right. If we lower the temperature, that is like removing heat. That's take towards. Take towards means removing heat. We will also shift to the right. If we increase pressure, we have to add up the coefficients of the gases on each side. And when I see a 1 and a 3 on this side, both with gases. So this side is 4 gas. I see a 2 with a gas, so this side is 2 gas. Increasing pressure will also happen to shift right because there is less gas on the right. Shifting right means that we are increasing what's on the right. Shifting left, if any of these had shifted left, what's on the left would have increased in concentration as a result. pH is negative log of the H plus concentration. Remember, we generally say that our pH scale goes from 0 to 14. 7 is neutral, where the H plus is equal to the OH minus concentration. Below 7 is acidic, where the H plus, which is the acid ion, is in greater concentration than the OH minus. They are always both present. And higher pH is the fact that the base ion is greater in concentration than the acid ion. Every number on the pH scale is a factor of 10. So if pH equals 1 and you want to compare it to pH equals 3, pH equals 3 is 100 times less acidic because it's 2 places away. Okay, there's 2 zeros in 100. If we want to compare pH of 5 to a pH of, I don't know, 1, let's not do 1, let's do 4. The 4 is 10 times more acidic than the 5 because it is 1 place lower on the pH scale. When we look at table M for indicators, table M, I'm just going to pick one indicator here. Let's look at bromothiamyl blue. Bromothiamyl blue says that from 6 to 7.6, it changes from yellow to blue. What that means is that before 6, it's yellow. After 7.6, it's blue. But in this middle range, it's green. So anytime you see bromothiamyl blue, if it's yellow, the pH is less than 6. If it's blue, the pH is more than 7.6, And if it's green, it's in that center range. Voltaic versus electrolytic. We'll do voltaic first. Voltaic cells are spontaneous. Redox reactions, where they are going to convert chemical energy to electrical energy. If we have our voltaic cell is a battery. If we pick a voltaic cell, and let's say we have two pieces of metal, usually they are connected by a wire to a voltmeter. The other thing that I've seen here besides a voltmeter is a light bulb. It's not light bulb, light bulb, to show that electricity is being given off. Don't forget your salt bridge for the flow of ions. Don't forget your electrons go in the wire. Remember, we're going to have the active anode, anode negative, and anode oxidation. The less active metal on table J will be the cathode. The cathode will be positive, and remember we have big red cat because the cathode gains electrons, gains ions, and gets bigger. Electrons are always going to flow in the wire from anode to cathode. If we are talking about the electrolytic cell, anode is still oxidation. Electrons still go in the wire from anode to cathode. Cathode is still reduction and still gains mass as well as electrons. However, electrolytic is non-spontaneous. Non-spontaneous? What? Non-spontaneous and requires a power source. The power source will cause the reaction, and we are going to take electrical energy and convert it to chemical energy. In this case, the anode will be attached to the positive part of the power source, and now the cathode will be attached to the negative part of the power source. So anytime you see power source, battery attached instead of a voltmeter or a light bulb, you're going to think electrolytic. Isomers have the same molecular formula. So they have the same numbers of C, H, etc. atoms, but they have different structural formulas. So for example, once you get to 4 carbons in the alkanes, this would be butane. And if we take one of the carbons and pop it on into the middle there, we can make methyl propane, which is an isomer. They each have C4H10 as their molecular formulas, but they are put together differently, so they have different structures. So that was everything that everybody asked me to review on that Google form. The next video that I will be putting together will be for that in terms of. Please make sure that you are studying daily between now and the Regents. Good luck.